Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss reflection and transmission coefficient. Let's begin. Reflection coefficient at an interface, that interface between two media, is defined as the ratio of reflected intensity to that of incident intensity. Let that be the interface of two media. Electromagnetic wave is incident on that of interface. After that, reflected, some part transmitted, k r vector, k t vector, angle of incident, theta I, angle of reflection, theta r, angle of transmission, theta t. So, according to our definition, reflection coefficient are that of interface, that interface separate the two media, defined as the ratio of reflected intensity to that of incident intensity is the reflection coefficient, or in another word we call it as reflectivity, or we call it as reflectivity. Reflectivity. So, reflection coefficient that is R is equal to the ratio of reflected intensity to that of incident intensity. What is intensity? Intensity is nothing but energy per unit area per unit time, that is the intensity. Here we consider reflected intensity means energy reflected per second per unit area. Okay. At that of interface where we calculate reflection coefficient. Next, incident intensity, that is energy incident per second per unit area. How to calculate energy reflected or energy incident per second per unit area? It can be calculated by using Poynting vector concept, or energy is calculated on the basis of average Poynting vector, and we consider that area as the area of cross section. So, the Poynting vector, in Poynting vector form, energy reflected per second per unit area is written as P r vector dot n r cap its magnitude. What is p r vector? P r vector is the pointing vector for reflected wave at that of interface, and n r cap is the unit vector along the direction of energy flow in that of reflected ray, divided by energy incident per second per unit area, again in that of pointing vector form, it is P incident n incident. Same thing, P I vector is the pointing vector for incident wave at that of interface, n I cap is the unit vector along the direction of energy flow in that of incident wave. Now, that pointing vector can be solved. What is P r vector dot n r cap? P r cos of that angle, that is P r cos theta r, angle between that P r vector and n r cap, that theta r, divided by same P I cos theta I. As we say, for that of reflection, theta I is equal to theta r. So, it will be P r divided by P I. What is P r? P r with the average energy under that of pointing vector, and in mathematical form, that is nothing but the magnitude of cross product of E r cross H r divided by, for P I, that is incident H I magnitude, incident electric field, incident magnetic field, its cross product with the value of that P r and P I respectively. How to evaluate that cross product magnitude? Come here. E r cross H r vector is equal to E r vector cross, in place of S r vector, that is epsilon 1 mu r under root n r cap cross E r vector. The relation between E vector and S vector is used, its magnitude. A cross B cross C formula can be used here. The constant term epsilon 1 divided by mu r, that is E r dot E r n r cap minus E r dot n r E r vector. magnitude ER dot NR. Since ER and NR are perpendicular to each other, so its dot product result as 0. Why? We write here as E vector is perpendicular to NR cap. Therefore, we obtained only that term as epsilon 1 under root epsilon 1 by mu r under root ER dot ER magnitude of ER square. For non-magnetic field, or we call it as for perfect dielectric media, for perfect dielectric media, the relative permeability is same as the permeability of free space. That is why it will be epsilon 1 divided by mu naught under root ER magnitude square. Similarly, the value for E I vector cross S I vector magnitude nothing, epsilon 1 divided by mu naught under root, that is E I incident. For amplitude term, we can use E O R, that is E I magnitude. These values are put it, that is epsilon 1 divided by mu naught under root, this is the amplitude term for that of reflected wave, that is O R magnitude square divided by, for that cross product magnitude, epsilon 1 mu naught under root E O I amplitude of that of incident electric field vector square. Cancelling numerator and denominator term, for epsilon 1 divided by mu naught under root, we have E O R magnitude square divided by E O I magnitude square, which is the expression for reflection coefficient, or we call it as reflectivity, which is the general expression for reflection coefficient or reflectivity. Next, transmission coefficient or transmittivity. Similarly, transmission coefficient is defined as the ratio of transmitted intensity to that of incident intensity at the interface between the two media, and here that media is non-conducting, or we can say non-magnetic medium. So, transmission coefficient, or we call it as transmittivity. by using the definition transmission coefficient denoted by capital T. This is the ratio of transmitted intensity to that of incident intensity. What is intensity? As I say in that of previous expression, intensity is the energy per unit area per unit time at that of interface. So, for transmitted intensity we write energy transmitted per second per unit area divided by for incident intensity, this energy incident per second per unit area. Come to that mathematical part. It can be shown in terms of Poynting vector. In terms of Poynting vector, it is written as Pt vector dot nt cap magnitude. For incident, that is Pi vector dot ni cap magnitude. So, its value as Pt cos theta t divided by Pi cos theta I, which is equal to, we put it the value of Pt as Et cross St magnitude cos theta t divided by for Pi Ei cross Hi magnitude cos theta I. The values are put at its magnitude. Similarly, we write epsilon 2 mu naught under root E OT magnitude square cos theta t divided by epsilon 1 mu naught under root E OI magnitude square cos theta I. Therefore, this one is equal to epsilon 2 by epsilon 1 under root cos theta t divided by cos theta I E OT E OI magnitude square, its magnitude square. This is the value for transmission coefficient T. So, transmission coefficient is equal to that much. See the expression for transmission coefficient expression. That the expression for transmission coefficient. Okay. These two are the general expression for reflection coefficient as well as transmission coefficient. By using these two general equations, we easily shown how energy is conserved during the process of incident, reflection and transmission. Case number 1, when electromagnetic wave obliquely incident. Here we taken that electromagnetic wave obliquely incident, then it is reflected and transmitted. Another situation it may be when electromagnetic wave normally incident. First we taken obliquely incident situation. When electromagnetic wave obliquely incident, either E vector is perpendicular to the plane of incident or E vector is parallel to the plane of incidence. When E vector is perpendicular to that of plane of incident, so the reflection coefficient at that of perpendicular situation plus transmission coefficient at that of perpendicular situation is equal to R perpendicular expression. R perpendicular expression is used, EOR EOI perpendicular square plus next T perpendicular expression is used, that one. So what is EOR EOI perpendicular? EOT divided by EOI perpendicular. These two are from the Fresnel's equations. As we have already discussed the Fresnel's equations and its derivations, 4 number of Fresnel's equations. When E vector is perpendicular to the plane of incidence, then these two are the Fresnel's equations, reflected to that of incident at perpendicular situation, transmitted to that of incident at perpendicular situation. Next, another 2 Fresnel's equations. When E vector is parallel to that of plane of incidence, reflected to that of incident when parallel situation, transmitted to that of incident parallel situation. We use Fresnel's equations at that of perpendicular situation. For EOR divided by OI, that equation is used, and EOT divided by EOI, this equation is used. So using these two equations and squaring it, as we consider for non-magnetic medium, so permeability at medium 1 and permeability at medium 2 is same to that of permeability of free space, that is mu 1 is equal to mu 2 is equal to mu naught. This is the permeability of free space. Come to this situation, in place of mu 1 we substitute mu naught, mu 2 again substitute mu naught, and taking the LCM in that of numerator and denominator side. So mu naught is cancelled out on these equations. So the simplified equation now written as epsilon 1 under root cos theta I minus epsilon 2 under root cos theta t divided by epsilon 1 under root cos theta I plus epsilon 2 under root cos theta t whole square plus as usual term. Similarly here mu naught divided by, in that of numerator side mu naught cancelled out, that is the existing equation. Squaring numerator 1 and denominator 1, here 2 epsilon 1 under root cos theta I whole square, that is 4 epsilon 1 under root square, that is epsilon 1 under root of that of epsilon 1 and only epsilon 1 cancelled out, we have under root of epsilon 1. Next 1 cos theta I 1 cos theta I cancel out. So, we have 4 epsilon 2 under root epsilon 1 under root cos theta t into cos theta I divided by square of that term. Taking the LCM, we have this one. Identity is used as a minus b whole square is equal to a plus b whole square minus 4ab. So, a minus b whole square, a plus b whole square minus 4ab plus this one, plus minus cancelled out. In that of numerator and denominator side the terms are same, this cancelled out. So, finally, we obtain r perpendicular plus t perpendicular is equal to 1. R perpendicular t perpendicular is equal to 1. What it signifies? It signifies that the energy is conserved. The reflection coefficient plus the transmission coefficient is equal to 1. Physically, we call it as energy is conserved. In similar manner, we can prove when E vector is parallel to that of plane of incident. When E vector is parallel to that of plane of incident, then another two pairs of Fresnel's equations came into picture, and putting these values and simplifying it under non-magnetic medium condition, we finally obtained this expression as R parallel and T parallel will be 1. Next thing, this is a discussion when that electromagnetic wave obliquely incident. Another situation for normal incident, when electromagnetic wave incident normally. For normal incident purpose, look that figure, when electromagnetic wave incident normally, then obviously theta I is equal to theta r, here theta I is equal to 0, therefore theta r ultimately 0, and then the angle of transmission also 0. So, the normal incidence condition, we have the angle of incidence is equal to the angle of reflection is equal to angle of transmission, which is 0. Same situation, r perpendicular plus t perpendicular, the values are put under that perpendicular condition by using Fresnel's equation. Fresnel's two equations at perpendicular situation is used. As we say, theta I, theta t, theta r are 0. So, cos 0 obviously 1, here the value of cos as 1, the equation changes to that form. And for non-magnetic, mu 1 is equal to mu 2 is equal to mu naught, in numerator and denominator side mu naught as LCM and mu naught again cancelled out, you obtain this form, that one is simplified, and finally use a minus b whole square, a plus b whole square minus 4 ab plus minus cancel out, square cancel out. So, we obtain r perpendicular plus t perpendicular is equal to 1. Similarly, by taking another two Fresnel's equations under that parallel situation, when E vector is parallel to that of plane of incident, and simplifying it, we obtain r parallel plus t parallel is equal to 1. What these two equations physically signify? It physically signify the energy is conserved. So, here with the help of this video lecture, we understand the concept of reflection and transmission coefficient. This is reflection coefficient or reflectivity, mathematical form. This is the general form of reflection coefficient. Next, transmission coefficient or transmittivity, the mathematical form in general way. Condition when electromagnetic wave incident obliquely. It has two situations, when E vector is perpendicular to the plane of incident, another situation when E vector is parallel to that of plane of incident. When E vector is perpendicular to that of plane of incident, we showcase that the sum of reflection coefficient and transmission coefficient is unity, which signifies energy is conserved. Similarly, we can show for that of parallel one, when E vector is parallel to that of plane of incident, that will be 1. Another case, when E electromagnetic wave incident normally, for normal incidence condition these angles are 0, and by using Fresnel's equations in these expressions under parallel and perpendicular situations, we can easily show it will be 1, that one also 1. So, with this useful and informative notes, let me wind up the session. Thank you.